Hello, what I want to talk about today is the alkene reactions that we've been studying in class. I want to talk about the mechanisms so that you can specifically see what's happening in terms of the regiochemistry and stereochemistry. And I know Klein goes over this, but I thought it might be helpful to see me work through these problems as well. So what I have on the board is an alkene that I think will enable us to see both regiochemistry and stereochemistry. Again, just a reminder, I have D here, which is deuterium. So we're going to use deuterium instead of hydrogen there so that we can see the difference between deuterium and hydrogen. Again, deuterium is just hydrogen with one neutron. So it's a deuteron, not a hydrogen. And again, we can watch that throughout the reaction. All right, so these are the four reactions I want to start with first. We'll do these, and then we'll do the other three so that you'll have all of the mechanisms drawn out to help you as you learn more about alkene reactions. All right, so let's do our favorite one so far anyway, which is addition of HX, right? So let's work through the mechanism so we can clearly see what's going on with the regiochemistry and the stereochemistry. So we're going to have the alkene nucleophile attack the electrophilic proton of HBr, right? That's going to break the HBr bond to give us Br minus and then a carbocation. And again, as we talked about in class, we're going to add H to whatever side of the alkene will then generate the more stable carbocation, right? And here we can add H to the side where the deuterium is or where the methyl is. We want to make the tertiary carbocation, so we're going to add it to where the deuterium is, right? So that we're going to end up with that carbocation. And the key thing about this reaction and all alkene reactions is that we've added H to the front of the alkene. We can also add it to the back of the alkene. And I think it's really useful when we're doing reactions like this to draw both of those out, right? So that we now have those two carbocations, right? And hopefully it's clear that those are enantiomers, right? So in the first step, when we add H, we're forming enantiomers, right? Now what do? Well, we have Br minus. And again, hopefully it's clear when we think about those carbocations, and again, you can draw this out, right, when you're thinking about what these carbocations look like. Don't forget that we should be thinking about the carbocations like that with their empty p orbital, so that now when the Br minus comes to attack these carbocations, the Br minus can add either from the top or from the bottom, right? So that we can get more stereoisomers out of this, right? So Br minus can add to this carbocation, Br minus can also add to this carbocation, and again, to each of those, it can attack from the front and from the back, so that we're going to end up getting a total of 4 stereoisomers. Right, so let's draw out what we get from these. So if we start with this molecule here on the left, Br minus can add from the back. It can also add from the front. Right, so we get those two molecules, right? And then we can do the same with this one here, right? We can add Br minus to the back. And we can add Br minus to the front, right? So we've added H initially to the front and the back. Now we've added Br to the front and the back. So we end up with 4 of these. And you should be able to look pretty quickly and figure out, if I actually put the H's in, there we go, that when we're adding HBr, that 2 of these are the result of anti-addition, 2 are the result of syn addition. Right, so here the H and Br have added anti, H and Br have added syn, H and Br have added syn, and H and Br have added anti. Right? So we get both syn and anti-addition when we do HBr, right? The result of forming a carbocation and there not being a preference for where the bromine is going to add, okay? And I encourage you to go through and verify that the 2 anti products are enantiomers, the syn products are enantiomers, compare syn versus anti, and those are diastereomers. Right? If we look at the sulfuric acid and water reaction, essentially the same thing is going to happen. Right? We're going to have the alkene attack the proton from sulfuric acid. Right? We're going to end up forming the same two carbocations. Right? And then water is going to add, and it's going to do exactly the same thing we did up there. So we're going to add water, then we're going to do a proton transfer, right? So water is going to add there. It's going to add from the front. It's going to add from the back, because again, we're going through the same carbocation. So we can just draw out what the products are going to look like. And again, they're going to look just like what we have up top, except OH is going to be in place of the Br. Right, so this enables us to form 4 different alcohols. And again, we can go through and look and say, this is the result of syn addition, this is the result of anti-addition, this is the result of anti-addition, and this one's the result of syn. Okay? So again, these 2 reaction mechanisms are identical. It's just, are you adding a halogen or are you adding water to give you an alcohol? Right? Exact same thing. Right? We're going through a carbocation. They're both syn and anti. All right, now when we look at these other reactions, we're going to see we have 2 different mechanisms. So when we look at what happens with the alkene reacting with H2 catalytic palladium on carbon, we first need to understand what happens when hydrogen reacts with catalytic palladium on carbon. Right? And the key thing is when these 2 things react, so when we have H2 and catalytic palladium on carbon, we're going to split the HH bond. So we're going to end up with pieces of palladium. So this is just a chunk of palladium on carbon. And there's a nice illustration in Klein about this, but what ends up happening is that you end up having hydrogen bonded to the palladium, so that there's no longer an HH bond. You end up with 2 hydrogen palladium bonds. Right? And then what happens when you do this reaction is that you have the alkene, and the alkene is going to react with the hydrogen such that you're going to make your 2 new bonds. And you do them simultaneously from the solid palladium source, so that you have the alkene attacking 1H, those electrons go back to palladium, and the electrons in the other palladium to H bond go to form the other carbon-hydrogen bond. So you're forming both of these bonds from the same side of the alkene, right? And this is a syn addition. They're both forming from the same face of the alkene, right? So that when you draw out what you're going to get for the product, you can have the H's adding from the back, and you can have the H's adding from the front. All right, both the result of syn addition. All right, so when you do this reaction, it is a syn addition. You do not get any anti. All right, and hopefully it's clear that these 2 are enantiomers, and you get a racemic mixture. Okay, so we get a racemic mixture of enantiomers. So that's the mechanism for H2 addition. If we look at this other reaction, this is hydroboration-oxidation. Right, for hydroboration-oxidation, we're going to have another different mechanism, right? So let's draw out what's going to happen here. So if we draw our starting alkene, right, this is a really interesting reaction, and it has everything to do with boron and how boron behaves. So what's going to happen with boron is that we're going to form the carbon-boron bond and a carbon-hydrogen bond simultaneously. Boron is larger than hydrogen, so boron is going to go to the less hindered side, hydrogen to the more hindered side. So we're going to form those two bonds, again, simultaneously. So the alkene attacks boron. The BH bond is going to form the new carbon-hydrogen bond, right? So we have arrows that look like that. And when we do this, we can add the B and the H from the back. Or we can add from the front. Right, so that we're doing a syn addition. Right, we're forming those bonds simultaneously, much like what we're doing in the hydrogenation reaction. Right, so we form these two, and if you look through Klein will talk about how those other BH bonds can continue to react, and that's definitely true. It's just going to be simpler if we don't worry too much about that. Just say that, yeah, those things can react. They're going to react exactly the same way. And then when you do the second step, which is the oxidation step, so hydrogen peroxide, sodium hydroxide, and water, when you do that step, you're going to oxidize the carbon-boron bond. Simply put, all you do is replace boron with oxygen. Nothing else changes. And so you turn that carbon-boron bond into an alcohol. Right? We don't need to worry about the mechanism. You can look in your book or online to figure out what that mechanism is. But all we need to do is replace B with OH, and there are no other changes. So no changes to the stereochem. All right, since the stereochem doesn't change, this is called a retention reaction. All right, and so what we draw is just the same thing we had before. Put OH everywhere that you see boron. Okay, so for this one, just replace the boron with OH, we get here. This one, replace the boron with OH, we get here. Right? And again, we have a racemic mixture, right? And if we look at what happened, we did a syn addition followed by a retention, and so the net result of this is that it's a net syn addition. Of H and OH. Okay? So this gives you an idea of what the mechanism is, thinking about regiochemistry and stereochemistry for these four reactions. All right, what I want to do is I'll make a video momentarily with the other three reactions, the two bromination reactions or halogenation reactions, and then oxymercuration, demercuration. So that'll be the next one.